Well, good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Huang, who is currently an associate professor at the Chemical, Biological, and Materials Engineering Department of the University of Oklahoma. He obtained his master's degree at the Nanjing Tech University in China and his PhD in chemical engineering at the North Carolina State University, where he also took a postdoctoral position. Some of his research interests include molecular modeling, confinement effects, and surface science. His research is focused on combining multi-scale modeling techniques to accurately estimate the properties of complex materials and systems through molecular simulation, with emphasis on adsorption, diffusion, and reaction at interfaces. Other focuses of his research are hydrolysis and catalysis reactions in metal-organic frameworks and confinement-induced high-pressure effect of nanoporous materials. So once again, welcome, Professor Huang. Thank you so much for being here, and feel free to share your screen and start your presentation.
So a small note that we actually recently changed the department name in order to attract more students. So now we call ourselves as School of Sustainable Chemical, Biological, and Materials Engineering. And we just recently started a new online master program on sustainability. So I have to get involved and prepare lots of exciting research or educational materials around the sustainability. So just a little bit of self-introduction. So this is how I was spending my last 20 years. So I was doing BS in Nanjing Tech and really fell in love with thermodynamics, which is the reason I moved on to my graduate school at Nanjing Tech. I was doing some Monte Carlo molecular dynamics calculation with Professor Xiaohua Lu. And at the same time, I was so lucky in welcoming Professor Gubbins his first visit to Nanjing. So we got connected, and he thought I may have some little potential. So this is how I moved from Nanjing to North Carolina and stayed there for very enjoyable 7 years, both academically or for our personal life there. So I was mainly doing learning ab initio DFT calculations, reactive force field to evaluate adsorptive processes together with reactions. Then I moved on to University of Oklahoma in 2014, and I have been there ever since. So the general scene we try to focus on in our study would be the fluid and solid domain. So we really try to utilize the theory of thermodynamics, kinetics, reaction engineering, and we try to understand those interesting domains by model and molecular simulation. So here I'm just listing those interesting topics on liquid separation, waste treatment, or valuable components recovery, so on. And most recently, we try to move in the direction of waste decomposition for the sustainability purpose. And I want to have this little figure to share a little bit of our department. As you can see that we have a very unique and very strong theory and computational team in my department. So we have very nice interconnection on all sorts of different skills, from ab initio, from atomistic, up to coarse grain, DFT, or finite element analysis. So we have 5 colleagues, and quite often we organize group meetings together, and we brainstorm crazy ideas, and we work together a lot. So this is what we are trying to achieve all together as a team on computational research for complex materials and complex systems. So this is the highlight. When I was interviewing quite a few years ago to University of Oklahoma, Professor Hall, she helped me to put up this slide. And I'm still using that slide. I have a printout copy on the wall of my office. So this is what we are trying to achieve eventually. So we try to develop some simulation methods that will allow us to bridge the different skills so that we can understand from ab initio all the way up to coarse grain. And then more importantly, in the chemical engineering domain, we really try to apply those methods to understand interesting and important applications to energy, environment, and health related topics. So if you check the keywords I have over here very quick, I'm having these three different colors. Number one is really the keywords from our engineering domain. So we have been interested in understanding the simultaneous adsorption, diffusion, and chemical reaction for those applications. At the same time, we are interested in the engineered materials, for example, graphene oxide, metal organic frameworks, and most recently, moving a little bit towards the polymer materials. And then the last would be the set of the keywords regarding the computational methods. So we combine the ab initio DFT calculation, Monte Carlo for adsorption, MD for diffusion, and then of course reactive molecular dynamics for larger scale reactive systems. Since last year, we slowly moved to the more sexy domain of machine learning and AI. We are still learning together with the other colleagues, but this is a really potential direction for many of us. So for this audience, I don't think I need to have this introduction slide, but for the computational study, we basically follow this very general trend. First of all, we try to develop the model of the materials or system of interest with the help of other level of computational studies or experimental guideline. And then we try to test the system to understand what is going on. Do we have to worry about adsorption only physical interactions, or we have to worry about both adsorption and reaction? So if that is the case, we need to worry about the reactive interaction, then we move on to apply other methods and reevaluate the system by looking at the reactions either at the electron scale or on the molecular or even larger scale. So we will switch the methods depending on the system and the properties we are interested in. So here, today, hopefully I will have enough time to share three examples from our recent calculations regarding interfacial reactability and interfacial reactions. And one is the recent work regarding morph. And we realize there is a funny mixture of the phase, of the water phase, that is super critical for the water-related hydrolysis reactions. So before I forget, I really want to acknowledge I'm here just talking, and all those very interesting results are produced by my previous students. And you can see that many of them are taking faculty positions. So I'm going to add a few new branches to Professor Gabin's, Professor Hall, their academic tree. So you're going to have many grandkids and in our domain, hopefully. And also I want to acknowledge to many of our dear colleagues over the years, ever since my PhD time. So many of them are providing experimental support. Some of them are working together with us on multi-scale simulation techniques and method development and so on. So I have been really fortunate in having their support over the years and treat them as my dear friends. And of course, I'm really grateful that the funding agencies are trusting us and providing financial support for those research topics. So I probably will not discuss lots of computational details. For example, maybe I will not even mention the force field and how large of the system, how many molecules will be there, and how long we calculate those things. But here I'm just having this slide to remind you that we combine DFT, combine adsorption and molecular dynamics calculations, most likely using those very popular softwares for all those examples I'm going to share. And we really try to do a good job and share with the community with what we learn from our calculation. So very typically, all of our papers, we have detailed supporting materials. And many of those, you can even find the calculation files. So I'm just having the list of those, and if you are interested in understanding more details, please feel free to email me and I can share all those files with you. So the first example is about water at metal surfaces. This is not a new topic at all. So people from catalysis, they have been studying this for a very long time. For example, I'm pointing you to a very nice review article in 2009. So people have realized in their calculation that for almost all metal surfaces, when you put the pristine metal in contact with water, liquid water, you are going to have this very nice first layer of water over here. And then interestingly, depending on the metal you are using, you may have the non-wetting or the liquid drop over there, or you may have the complete wetting for the case of gold, AU100 surface. So when we are looking at this system for our NSF project, we try to understand this is great, but as the engineer, we try to manipulate, we try to control, and we try to understand what would be the potential application to the engineering field. So really, we try to say that here is the metal, and I'm going to have water, but what if I'm going to create some kind of defects and I manipulate the solids? Are we able to manipulate the liquid behavior on top of that? So this is what we try to understand in the first set of calculation. So we try to apply the so-called strain to the solids. And for us doing computational study, this is very easy. So in order to mimic the strain, we just change those metal atoms. We just move them a little bit closer, or even closer, to mimic the amount of strain the material is going to receive. So as you can see from this slide that when we don't have any strain applied to PD, then we reproduce the results reported in literature. And if we keep adding from 1%, 2%, all the way up to 5%, clearly you can see that it's changing. So you always will have the first layer of water, but then because of the strain, something magic is happening. You are going to convert the wetting property of that layer of water, and now you are going to have the full wetting of that system under 5% of strain to the solid material. And I hope it's not surprising that we can achieve the same kind of trend to the other material. Here, when you look at gold, pristine one will have the complete wetting. And when you move those gold atoms a little bit closer to mimic the strain, you're going to see, oh, I'm going to have a little bit of hydrophobic behavior over here, starting quite early on 2%, then all the way to 5%. So this is really the set of the first one I'm having. And by the way, I'm having all those slides numbers. So if you think it's not too convenient to ask a question during the presentation, please keep the slide numbers so we can come back and discuss on those. So really from the engineering point of view, when you try to look at the strain as a function of the contact angle, we clearly see that we can manipulate. By applying the strain to the solid, we're able to tune the liquid behavior. But how or why this is happening? Or if we are able to achieve that, what would be the interesting application? So in order to do that, we are thinking of the other thing on the very basic idea that in the application, it's kind of rare that you use a purified metal. So many people are using alloy, and here we just try to put the two metals together, call it as a bimetallic interface. So this is of great potential in many material science, engineering, and chemistry applications. So what's going on if we naively put PD and AU together to form a new interface? And of course, in order to do that, you have to do something. And we are forced to do something, both in real application and in computational study. That is simply because they don't match in their lattice constants. As you can see that AU is a little bit larger in their lattice constant. So when you try to fit them in the one single plate, you have to compress. And that's the natural requirement for the metal constraints. So we estimate the constraint in order to put them together, the pristine PD100, the compressed AU100, we have to apply that much of strain to gold. And that's corresponding to 0.2 gigapascal. It's slightly large, but maybe the aerospace and some extreme applications, they are in the domain of that strain. So here is the model we are having. We compress the AU, we maintain the pristine PD, and that's a model. So what will happen if we put liquid water on top of that? So here is the calculation trajectory. So we have those gold and PD relaxed but constrained afterwards. And then we apply 1 nanometer thick of a water layer. On top of that, we have 8 nanometer of the vacuum. And we run the calculation. We allow the water molecules to be flexible. There's no constraint at all to all those water molecules. And now you can see that naturally, you still observe the first layer of water on both sides. And then interestingly, you can see that the other water molecules are not too happy with the water layer on PD. So they try really hard to move all the way on the gold side. And you may see a few molecules remaining over there. That's purely due to the periodic imaging. Run the calculation long enough, you can simply ignore those remaining water molecules. So that is what we observed, and we thought, hey, there's some kind of wettability transition, and I'll show you in a minute why we call this as transition. And we try to understand who is responsible for that phenomenon. So if I quickly summarize, so this is the initial setup of the calculation. And if we run the calculation at the ambient condition, 300 Kelvin, 1 ATN, after about 15-20 nanoseconds, you would observe this very nice and uniform distribution of a single layer on PD, but then a single layer together with the remaining liquid water drop on top of gold 100 surface. So what is going on? And if you recall really quick a previous slide, if we are treating those separate metals, we would expect the PD, you are going to have the first layer of water, and on top of that, you are going to have some hydrophobic behavior. And if you are using pristine gold 100, again, a first layer of water, then on top of that, you are going to have complete wetting. But interestingly, if you compress gold a little bit and putting it together with the pristine PD, then you are going to convince the liquid drop initially on the PD 100 surface, move all the way to the gold 100 side. So that is something we observed. And we really try to understand what is the fundamental mechanism behind this. So we come back, we try to imagine what could be the possible reasons. This is still the substrate, and nothing is flexible, nothing is changing. We do have this one layer of liquid water layer or solid water layer, and then apparently they are very different from each other. So that's the only possible way to convince the other waters to pick up a side, right? So we thought that the unique secret shall be within this single layer of liquid water. So let's try to see what is going on. So this is what we did. I'm going to show you really quick without even explaining the details. But here, please keep an eye on the comparison. So all those following analyses are done to this first layer of water on both PD 100 and gold 100. And we try to see which one is more perfect. And you can naively thinking that if I'm going to have a perfect layer of water, they really don't need to have any extra interaction with other water molecules to have the layer stabilized. So the perfectness is kind of the index. Do they need the interaction from other water or not? And if they don't, then they really have to kick the other water molecules away from their top surface, right? So this is what we try to understand in the simple and plain way. So here we are looking at the density of the first layer of water. As you can see that we can quickly conclude that on PD 100, we are going to have higher density of that unique layer of water molecules. What if we move on to look at their configuration, simply because the water is very unique in forming hydrogen bonding and having the quite nice structural requirement. So here we try to look at the dipole moment as well as the OH vector, purely to understand their structural perfectness, to see which one is better. So now when you look at the dipole of that first layer, again, PD 100 surface will win. That layer will have more perfectness of that dipole configuration. And it's not surprising at all, I hope, that now when you look at the OH vector or configuration, sort of another index of this structural perfectness, PD again is going to win. And now if you move on to look at the other heat map, coupling the two, then again PD is going to win because it's really focusing on one kind of configuration versus you may have different options on the gold 100 facet. And then if you move on to look at a little bit of dynamic process, recall that for our calculation, we allow all the water molecules to move around. So we can calculate the time correlation function to understand all sorts of network, self-diffusion, lifetime, those properties, so on. So it's not surprising that PD is going to win all the time. So I'm going to skip those detailed analysis. I'm going to refer you to our publication later on. So that is the kind of the interesting thing, including the free energy profile. Again, PD is going to win. So in the end, we are able to use those analyses, and we try to come up with a very general conclusion. Number one, the first layer, that stability, is really the dominating factor to the near layer surface wettability. Number two, applying the mechanical stress, whether to the pristine single atom or the multiple bimetallic or even other systems, you are going to nicely redistribute the other water molecules beyond the first layer of water. So here I'm having this reference paper we published with my students, and then pay special attention to the quite nice, in our opinion, the 32 pages of supporting information. And we also published a review article following that paper in another year. So that is the first example I want to quickly share with you. So water, when they are coming and interact with the metal surface, they are going to form the first layer. And beyond that, you're able to manipulate, because of that first layer, the wettability of other water molecules. And the second example is also at interface, but no longer to metals, but to organic, sort of a little bit cheaper materials. So here, I want to share the calculation we finished on this so-called carbon nitride. So basically, this is a two-dimensional material where you are going to have the alternating modification of nitrogen elements to the substrate. And then it's not a complete perfect. You are going to have the hexagonal type of core along the two-dimensional substrate. So the reason we got interested in this is really because of the small molecular interaction, here specifically for the hydrogen peroxide. So I'm having here with a quick introduction that this is a very interesting system for us to study, because of the sustainability, energy-related concerns. So the traditional method is excellent, supporting us for the past 80, 90 years. But now it's a time to re-evaluate the whole process to see if we can do a better job regarding sustainability and energy cost. And over the past 8, 10 years, people are really proposing lots of new possibilities regarding this reaction, including the electrochemical, photocatalysis, or even direct synthesis if you have a really good catalyst. So we got into this with a visiting PhD student and my collaborator from Zhejiang University of Technology. So here we try to look at what people have studied in the literature. So normally you are going to have oxygen and hydrogen as the reactants, and you identify a really excellent catalyst. And then in the liquid phase, you are going to have the direct synthesis of hydrogen peroxide. So when I was introduced to that reaction, my first impression is, hey, there is some potential concern. Why? Because by a quick analysis from thermodynamics point of view, you're going to have 2 gas reactants, and you are going to utilize a solid catalyst. And the whole system is on the solution phase, meaning you really have to convince the 2 gas species to have decent solubility or mix them well in the solution phase and move around to find the catalyst. So I naively thought there might be some improvement if we are going to replace the hydrogen donor by liquid water. So at least water will be there. They don't have to overcome the barrier for the phase mixtures. So what I proposed was to study this reaction. So instead of having oxygen and hydrogen, let's do the trade. Let's still use oxygen, but we are going to have liquid water. So now the problem is, can we find a really interesting catalyst to help and promote this reaction? It turns out that in the literature, people have explored, mostly from experiments point of view, the interesting potential of this carbon nitrates. And here I'm showing this schematic illustration of the material. So again, it's 2-dimensional. You can think of graphene sheet. You're going to have very nice pattern of nitrogen and carbon, and you are going to have a decent pore throughout that single plane. And in the experiments, people are able to really synthesize and produce this material much cheaper than graphene. So it has a great potential for the real application for future hydrogen peroxide synthesis. And on the other side, it's straightforward to this audience that we just go ahead and apply equal molar of oxygen and water to the system. And we just run the calculation at the ab initio level, either through AIDFT or AIMD, to see what will be happening if we allow the water and oxygen to interact with carbon nitride. So to us, there are some interesting questions to address, including whether this is a one-step reaction or they have to take some order. And if there is order, then which one is going to lead the reaction? Whether water interaction with carbon nitrate to initiate the reaction or oxygen will lead. And of course, what would be the role, the barrier and the exact mechanism on that solid substrate? All those questions we try to have some understanding by computational study. So before showing the results, I really want to show you these 2 very nice reviews. As you can see that we are having 2 very simple molecules, but the potential mechanism involved is a headache. As you can see, you could have 2 electron process, 4 electron process coupled with multiple intermediates and the rate limiting steps. On the other side, I want to quickly show you that really depending on the catalyst you are using, it could be a whole complete different story. So on this review for this PT as a catalyst of the reaction, really the oxygen adsorption is the initial step. But you'll see in just a minute that in our case, if we are not using noble metal as a catalyst, then water is going to lead us to the reactions. So I'm going to show you some results, not really in a systematic way. Please refer to the email me if you want to have the files and more discussions, so on. So here is a small trajectory of our ab initio MD calculation. As you can see that by the nature of LMD, we shall be able to capture the exchange of the protons between water molecules, the free water molecules, and the OH after the initial water dissociation. I want to add that initially, this is a pristine theoretical model of carbon nitride. There shall be no hydrogen, no OH group. And they are there because of the first batch of water dissociation. So if we move on, the first result is that we have to allow water to lead the interactions. We've done both water or oxygen, and we realize that only when we have the water association can we then move forward to the following steps. So when you look at water, easily you can tell that, oh, there's a water dissociation. There's OH group over there. You're going to have this not yet dissociated water, but sort of chemisorbed water. And nearby, you are going to have another sort of free water from the liquid phase. All the other molecules are removed so that we can clearly see. So basically, after the first batch of the interaction from LMD calculation, we realize that we are going to have different water molecules. So how do we distinguish those? And I apologize if you have some trouble with the color, but the basic idea is we try to really color the oxygen and hydrogen of different water molecules, whether they are at the surface, chemisorbed, or in the liquid phase as a free water molecule. Then we can follow the color so that we can easily analyze what is going on. So this is the first batch. So we have to have the nicely activated water over there. As you can see, for this water molecule, the OH bond, they are activated. So when they have some other offers, they're able to break the bond and donate the first proton, right? And that is exactly what we observe. So if we try to look at this screened local domain, so you can see that is the oxygen molecule. And the oxygen molecule is moving around to receive this. We probably have to wait and replay that one more time. Uh-oh. So you can see that is the oxygen, and we are going to have activated water, and we have nearby free water. So the mechanism we observed is really through the proton transfer, where this oxygen is going to pick up the first proton very easily from the chemisorbed water. And that water is happy because now it's going to be the OH group at this side and more stable than the chemisorbed water. But what will happen when you have the intermediate, this OOH? If you have to move it around for some distance, waiting some time, then it's hard because intermediates usually they are not stable at all. Luckily, we are going to have the nearby water together with other water. They are going to form the so-called water cluster proton transfer mechanism. So it turns out that the intermediate OOH does not have to move too much, but will stay there and quickly pick up other proton to form the final product of hydrogen peroxide. So if you allow me to go over that a little bit, so you can see this is oxygen picking up the first proton from the chemisorbed water. So there it's forming, and now you can see this is the intermediate And then in step 4, the intermediate is trying to talk with other water molecules. Hey, can you give me the other proton so I can be stable? And those water molecules say that, hey, let me check with my friends if we can achieve that. So they talk with each other, a few molecules nearby, and then eventually you can see they are going to exchange involving 3-4 molecules nearby and achieve the goal. So this is the final product finishing the reaction. And by the color, you can see that the 2 protons are coming from different water molecules. And for that reaction, they have to involve 2 adsorbed water, and some local free water molecules will help to speed it up. And of course, I'm just showing you some snapshot from the exact trajectory, and we have identified 3-4 potential mechanisms, all involving this very nice proton transfer mechanism of water clusters. In the biology research field, this is known for decades. And I think in the chemical engineering, in chemistry, we have not paid close enough attention to that potential proton exchange chain. But this is extremely, extremely useful for this reaction we studied. So here I'm going to skip that. So basically, this is the step: activation, intermediate, and then the proton transfer. And of course, we have to realize that the proper confinement to have the proper activation, so on, would be really important. And that is the paper. If you are interested, please feel free to read and download the relevant information. So this is the second example. So water is not only to form the perfect layer, but when you change the solid, they are going to form the very different interaction, activated and with other friends ready to donate through the proton exchange mechanism. And then there's some other recent calculation towards morph. So morph, we can naively thinking of having both. You're going to have the metal component, you're going to have the carbon inorganic feature. So what's going on if we think about that material with water? So for this, I want to quickly bore you with a little bit of introduction. So for the material we are studying, it's called the zirconia type of morph. And the zirconia node is showing over here. So this is not a single metal as a node, but the metal oxide. And then because of the metal, you are going to have the unique feature when interacting with water. You are going to have chemisorpted water, you are going to have the water dissociation, and even to the inner core, you are going to have the alternating OH and oxygen. So in the literature, people refer those sites as mu3O or mu3OH. And then, of course, they describe the node together with the available OH group to the zirconia sites and the chemisorpted water. So this is just the node itself. Now, when you provide the organic linkers, and please excuse me, I don't have the full name of those BDC, BTC, but those are just organic linkers. And when you put them together, you are going to form 3 interesting zirconia morphs. They have the unique name to who discovered them, the UIO66 and U1000 and morph 808. So quickly, you may have the same idea as we did. Oh, this is the same family, very similar chemistry or very similar structure. You could explore all sorts of features, right? Starting from the pore size, starting from the chemistry, starting from the defects, starting from the mixtures, whether it's liquid water or water with something else. And for the research grant we receive, we do study all those. And if you are interested, please check out the publications from us for the past 3 years. We will check all those one by one. But today, I want to really focus on, by the next 5 minutes, I hope I'm doing okay with my time. To quickly share with
Paul.
you.
Yes, Paul. Okay.
Thank you, Fred, my boss. So here, I really want to quickly share with you this NU1000. Why? it's kind of a nice philosophy. We call this as in between. So in between means it's going to have larger, not too small, not too huge for the structure. In terms of the chemistry, you can see by the topology or the saturation coordination of the nodes, it's also in between, not too small, not too fully saturated. So we thought that for this type of in-between structure, we may have more tunability to water molecules or any other species inside. So that is indeed actually the case. So before jumping on the results, I want to just quickly refresh you by the structural feature. So for all those three morphs, they have both mesopores, which is on the order of 3 nanometer in diameter, and then those micro nanometer type of triangular pocket. So here you are looking at from the top or from the side. So they are kind of interconnected. You have to move from one mesopore to the micropore or mesopore to micropore in order to jump along the same type of pores. So when we pick up the project, of course, we have to understand how many water molecules we have to put if this is to mimic the saturation. So here we have been working together with our dear friend, who is also a child from Professor Gubbins, a senior academic brother from University of Pittsburgh. We have been working together on this. So we utilize their new developed refit force field for water and OH, and we run the GCMC grand canonical Monte Carlo calculation to understand the absorption isosome. And again, please refer to the other publication for the computational details. But interestingly, we realized with the help of a quite nice review paper by Krista Walton from Georgia Tech, that if we think from the absorption community, we have the so-called match of the absorption isosome. Here I'm just showing you three. Number one is the strong hydrophilic absorption isosome. So if you observe this type of absorption isosome, then the material together with the species would show the hydrophilic feature. And if you see the strong hydrophobic, this type of absorption isosome, then this is the indication of the strong hydrophobic for that system. And if you have this kind of in between, this is called type 5 to the absorption community. This is something in between. And we are extremely happy because we pick up NU 1000 by the naive thinking of something in between. So now it's good. We are having the exact display of both hydrophilic and hydrophobic. Now let's move on to see what's going on. Again, this is absorption isosome. The red is from experiments. The blue is from our calculation. Sorry, I forgot to add the note. So you can see this is quite typical of the type 5, confirming that we have something in between in terms of hydrophilic and hydrophobic. So what's going on for water? So I'm going to quickly share a few slides to convince you that water is having some non-uniform behavior over there. So here is the self-diffusion of water as a function of water loading. So we just add a little bit of water all the way up to saturation absorption. As you can see that compared with bulk water, this is the bulk water self-diffusion. Now when you have water in the NU 1000, it's weird. For some directions, the water is kind of confined. They are finding their attractive sites and they stay. For the other direction, they don't want to stay and they leave really quickly. And that kind of trend is really depending on the water loading. So something weird or interesting is happening over there. So naively, we think that, oh, we may have different types of water. So let's try to figure out if we are able to identify those water and their behavior. And again, we look at their preferential residence, so on. So this is the residence analysis, again, by a function of water loading. So it's really depending on how many water molecules you have. They would initially prefer the small pore and then slowly transit to the other larger pores. And they have the strong preferential. And of course, this intermediate loading is kind of the transition point. So if I show you some snapshot really quick, this is our calculation snapshot. If this is a low loading, starting from the larger pore, eventually they will stay in the smaller pore. Those are from the calculation trajectory. And if you are having the intermediate starting spread out in the homomorph, then in the end, they are going to stay absolutely in the mesopore. And if you slowly increase, then you start to feel the other micropores after the mesopore is completely occupied. So this might be the most interesting slide. And thanks to my education from Professor Hall and Professor Gubbins, we try to look at this very simple radial distribution function and couple that to potential structural feature. So I have these two sets, but they are more or less identical. You may realize that whether they are on the same scale or they are on the different Y scale because of the density difference. So basically, the lower part is easier for us to have some conclusion. So we try to calculate the pure vapor water, RDF. So this is the pure water vapor. This is the liquid water where you are going to have the first strong peak coupled with the two and the second and third peak, indicating the hydrogen bond network. So now when you compare using the two as a reference, looking at water as a whole in the morph, you realize that, hey, it's not a vapor because you are going to have the small bump. But at the same time, it's also not perfect liquid at all because you only have some weak second peak, maybe have some small bump of the full saturation, but definitely not a well-developed whole liquid phase. So that is kind of the most strong evidence we have out of the calculation that when you have water, whether it's intermediate, whether it's full loading, you definitely will have some interesting non-liquid water molecules. And I have this, although I'm not the expert on MMR, but I take it for granted from my dear colleague from UNC Chapel Hill, Professor Yue Wu. He was very excited about our calculation results because they were puzzled by the MMR chemical shift. And very clearly, they see the second peak over there is shifting, whether low loading to the full saturation. This is definitely the evidence of two kinds of water group over there. So I hope by this quick analysis, I convince you that we are able to pick up this very unique NU 1000 sort of in between for both structural and chemistry features, and we are able to identify both liquid and vapor. I probably will skip this because we are still in the process of publishing this paper. So this is hopefully to tell you why. So now we have liquid water, we have vapor water, and we are not really interested only in water, but we are interested in the hydrolysis reaction. So when you have the liquid water, they are going to form the potential proton exchange network. When you have this closer sort of singular or vapor water, they will initiate the reaction for the following chemical warfare agent decomposition. So that is actually the secret of why we are interested in this. So hopefully I can share the results very soon. We are in the process of publishing this paper. So here we study the water mixture together with sarin and soman, and we find a very interesting, quite unique results due to the water, two different types and their unique residence either in the smaller pore or in the larger pore. So I'm going to skip that and skip reading this, but generally I hope that you receive the message that if you are having the combination of metal and the inorganic part, you may tune the hydrophobic and hydrophilic properties, and you could find these very unique two types of water coexisting, working together to achieve the following reactive applications. So again, this is a paper. You can find more details regarding the system. And I don't have a summarizing slide, but I want to really thank you for this opportunity and allow me to share our recent calculations. And we really look forward to future collaborations, either from experiments or computational point of view. One group is not enough to explore all those interesting parts. And with that, I'll stop my talk, and I'll be happy to answer any question. And apologize if I'm using a little bit too much of time. This is truly the last slide. If we have students who are interested in visiting me for a PhD, for a postdoc, or even for half a year, I have some budget to support out of the two recent grants from Department of Transportation and also DTRA. Thank you so much, everyone, for your attention.